Sorry, so you'll have to review some of my older lectures for that. But here we are. It is week 3 for us, and Wednesday is basically the halfway point of the quarter, which is crazy, right? Like 6 weeks, it goes by really fast, right? I'm always surprised that summer session is as crowded as it is, because we always talk about the quarter system being like this, like always flying by. Like the 10 weeks seem to go by so quickly, and then you come into summer and it goes even faster. And so it's stressful for students. It's also stressful for the teachers, but here we are. So anyway, on Wednesday we have our midterm exam. It's already here. And so I started, whoops, oh dear. I created a list of topics that I will have on the midterm exam. Let's see if this connects. Okay, so I guess if you have questions about the topics on the midterm exam, today is the day to ask, because the next time we meet will be the actual exam. So I'm looking at basically maybe like 7 pages of exam. It's going to be, you'll have the full kind of hour and 50 to complete the exam. And so anyway, we'll go through each of these things. You got questions, I will answer them. Okay, so the first thing says, find the gradient of some function with respect to a vector in matrix notation. Okay, so for example, find the gradient of the OLS function with respect to the vector W. Of course, it will not be that. But so, maybe what will be helpful is if I just kind of say, like, refer to this lecture. So this topic was covered maybe in pages the first lecture, pages 45 to well, look at page 45 and then look at, I guess, pages 52 to 55. So I'll update this, okay? Okay, so I'll say pay attention to lecture summer lecture 1-1, page 45, and pages 52 through 55. Great. Is that all right? Okay, so you'll have some kind of function. It'll be given in matrix notation, similar to OLS loss, but not exactly that. And you'll find the gradient with respect to the vector, okay? And again, as in all of these things, I strongly encourage you to write the dimensions of all of these things to make sure that they line up, okay? If you don't write the dimensions and you do something wrong, like if you do tx or something, okay, where the dimensions don't line up, you'll lose points on the exam, okay? So whatever you write, make sure, I'll say make sure the dimensions line up correctly. Okay. All right, number 2, find the numeric estimate of a gradient. I'll provide some function which takes a vector as an input returns a scalar value, okay? And then I'll provide a current value of W or whatever, okay? And then you'll estimate the gradient numerically by perturbing the elements of W one at a time, okay? And I think I already gave you this warning, but once again, a very common mistake, and I don't know if I'm making it too easy by telling you the most common mistake last quarter was that people changed like both elements at the same time, okay? You have to change one, one at a time. Change elements one at a time. Okay, and then here, let me just find which lecture that was in. I'll say it's like page 75. These slides are so long. Okay, so basically slide 73 and to 77, 73 to 77. So pay attention, I would say very closely to this. So this is summer lecture 1-2, pages 73 to 77. Now, part of me is dying a tiny bit because I want you to study more than just these slides, but I'm trying to be nice, okay? It's summer, I know it's stressful, so. Yeah, question?
How do we do number 3?
How do you do number 3? Yeah, you'll do it, okay?
I don't know how to do manual gradient.
Yeah, so we'll do, well, I don't know, we'll take a look, okay? So basically, I'll give you a function, right? And then you find the gradient, right? Can we find the gradient? Right, so we can do that. And then you'll just punch the numbers in, okay? Let's see. Where is, I can't remember what, okay, wait, this is the regularization, that comes later.
When you find the gradient, and then you subtract by lambda times the gradient.
That's exactly what we do here. Let's,
Okay.
yeah. Okay, so this is what we did. All right, so here's a manual example. All right, so I guess you can look at slides 41 through 45. Okay, so this is summer lecture 1-2, slides 41 through 45. Okay, so here I did one iteration manually. Okay, so this is the gradient descent algorithm. You're currently at location W at time n, and you're going to, the next iteration is our current location minus lambda times the gradient at our current location. Yeah, question?
You have to draw like a graph.
Yeah, I'll probably ask you to do that, okay? Huh? No, so I'll probably draw like a contour plot, and yeah, if you have a ruler, that's fine. I mean, this is a case where a straight edge is probably fine if you want to just use like a credit card as a straight edge. That's probably fine. You don't need like a 12-inch ruler on this thing, okay? It's gonna be a small thing, okay? All right, and so here's the function, right? So here's a arbitrary function, and we took the gradient of this, right? And so I'm hoping you can figure out the gradient of this. The gradient of this, because it's in 2 dimensions, is the partial of f with respect to x1 and the partial of f with respect to x2. So this is a vector. You see the comma, there's a vector of 2 elements in here. Okay, so that's the gradient. And then so if we say we are currently at location -5, 4, the gradient at -5, 4 is this, all right? And then to do your manual gradient descent is you take your current location, subtract off gamma times whatever this thing is, the gradient at that current location, okay? And then you do this, right? And then if you had to do a second iteration, all you do is you would take this, you recalculate the gradient at this location, and then you update it, okay? It's not too bad, okay? But but I'm hoping it forces you to kind of study your notes again, review all of this stuff. Okay, cross-validation, okay. So leave one out, cross-validation. So I'm going to provide a very small data set, maybe 3 or 4 data points, okay, in probably 2 dimensions. So I have to kind of tailor all of these things so that we can do them by hand. Otherwise, it's too hard. Okay, and then I'll provide like a model, maybe a model or models, okay, trained on points, you know, like A, B, C. And then you'll find the error on point D, okay? Because this is leave one out cross-validation, right? So that means we're using 3 of the points for the training set, and then the last data point is the validation set, okay? And so here, I'll provide you the equation. You don't have to like do least squares regression on the 3 data points yourself, okay? I guess if we had like 3 data points and you only had 2, it would be reasonable, but anyways, you got to use like point slope form, and that's annoying. So, all right, so I'll give you the model that's trained on all but 1 data point, and you'll find the error on the remaining data point, okay? And then you'll do this for all 4 data points. You'll get like an overall cross-validation error, and then you'll probably do that for the different models or things like that, okay? I don't think I don't have an exact example of this by hand in the slides, okay? But the leave one out cross-validation, that information is, well, it's at the end of the week 2, I believe. No.
Actually, before all this stuff.
It was before all of this stuff?
That's it. Week 1, lecture 2.
Oh, here it is, yeah. Okay. Yeah, okay. So, oh, yeah, it was at the end of the first lecture. Oh, no, I guess. No. Just at the beginning of the second lecture. Okay, so it'll be probably something similar to this, okay, where I provide the plot and the error here, and you'll find the error, okay? So I'll provide, maybe not the plot, but I'll provide the equation of this blue line, and this blue line, and this blue line, and this blue line, and you will figure out the amount of error, okay? And my recommendation would be to review your homework, is it homework 1 where you had cross-validation, I believe? Okay, homework 1, cross-validation problem. Okay, maybe try it manually with a tiny data set. So far, so good? Okay. And then number 5, a regularization problem. I'll provide another small data set, 3 or 4 points. And then I'll ask you to find kind of the ordinary least squares loss, the lasso loss, the ridge loss, okay? So I'll give you the data points and maybe some parameter estimates. And this is all... This is all in here as well. So we got the regularization. I guess you're, page 87 and 86, or 87, 88, and then I guess 87 and 88. And I can't ask you to do plots like that. Okay. All right, is that okay? So mostly stuff from the first week, okay? The second week we spent on neural networks. And I was debating what I should do here. All right, this is me thinking out loud, okay? So I decided I will not make you do back propagation, okay? You have to do that in your homework, okay? So, you know, you have a homework problem where you're going to do back propagation to figure out the gradients for the bias terms, okay? So you're going to have this thing with bias terms. And we'll do that in the homework. I won't put that in a test setting. I think it's a little bit cruel. So I will not put that on the test. But I think this is what I will probably do, okay? We'll have a simple neural network, okay? With maybe this is all, okay? Somewhere around 2 nodes in input layer, around 2 to 3 nodes in the hidden layer, plus bias terms, and then 1 to 2 nodes in output layer, plus bias terms, okay? And then this is what I'm planning on doing is I will provide a small data set, okay? And then you do forward feed, okay? Oh, here's the other important part. Very simple activation function, okay? The sigmoid, it's a simple function, but it's a pain in the butt to do when you're manually calculating it. Like to have to do like 1 plus e to the negative t and then 1 over that. That is a little bit of a pain. So probably my activation functions will be something like f of x equals x. That's the identity, okay? Or f of x is equal to x for positive x and 0 for negative x. Okay, and that's called the ReLU. All right. So it's a very simple simple function. So you know there's still a lot of like stuff you have to do because you got to like do the matrix multiplication. So I'm just trying to make your life a little bit easier by doing a simple activation function. Okay. Okay. A small data set, you do forward feed, and then the other part is I think I will ask you to estimate one of the gradients numerically. Okay, you know, by perturbing each element by 0.01 or something. Okay, and again, just like estimating the gradient numerically for the other problem, make sure you do it 1 element at a time. Yeah. Okay. Okay, questions? Yeah.
So are we allowed to use calculators?
Yes, of course. You will definitely need your calculators, okay? But it will be closed book, closed notes, okay? You gotta use your heads. And then I'll also send out a seating chart, okay? it's solved or it's alleviated a lot of issues I've had in the past. Okay, yeah.
Also, so like, are we gonna do like any coding related?
No, I'm not going to ask you to do code in the paper exam. All right? Yeah. Question.
So forward feed just means we plug in the values into the first node, and it goes to the second node and the third node, right?
Yeah. That's it.
Like backpropagation is one of the easier things we've done in this class. It's just a derivative.
I mean, I disagree, but yeah. I mean, yes, if you want to say it that way, it's easy, but it's just a derivative. But I mean, you know, we can just say, oh, machine learning is easy. It's just writing a few loops. So, so you know, I mean, I think you know this. I think the forward feed, the ideas are simple. Okay, there's going to be a few computations. Estimating the gradient numerically, I think, you know, conceptually, I think these are all not terribly hard. But at the same time, there are certain kind of mistakes that students make that, you know, maybe reflect a little bit of a misunderstanding of an essential topic. And the hope of this test and this whole course really is just so that, you know, if you were to apply for a data science job where there's machine learning involved, and that during the interview or the technical interview, if they ask you to just explain one of these algorithms that you're doing, you can explain it more than just saying, oh, I just type in neural net, nnet into R, you know, and I don't really know what's happening. You know, neural networks are super complicated, and I think even if you just understand just the basics of it, you've got an advantage over people who don't really understand the basics and just plug in something into some package because that's what you do, you know? I mean, there's pros and cons to the dumbing down of of machine learning, okay? And like if you learn Python, there's this excellent package called sklearn, okay? And that powers most of machine learning in Python. And it's really great, and they have a simple form, and the data all comes in, and you do like, model.fit, model predict, and all of this stuff, and it does a great job. But because they've made it so simple, you can try out like all of these different models without knowing what any of these models actually do and what the subtle differences are. All right, and so you know, I think this gives us just a little bit, just a sliver of understanding, right? Kind of just like your introductory physics class gives you just a slight glimpse into like how stuff in physics works. You know, this just gives us a glimpse into that, but it helps us understand some of these kind of more. It gives us a framework for these broader concepts. Yeah, question.
So what kind of conceptual questions?
Yeah, you know, the conceptual questions are conceptual questions, and I don't want to tell you what questions I'm going to ask, all right? I already feel like I'm telling you exactly what I'm going to ask, okay? So the conceptual questions, we're going to keep that a mystery, and my recommendation is just review the notes. Yeah, it'll be stuff like... but not this. I don't know.
Or just like the structure, would it be like free response? Or
yeah, it'll be free response. It'll be like a short free response. You know, I'm looking for like a one sentence answer for most of these things. You know, like I don't know. Here, okay, like if for the lasso loss, if gamma or lambda is 0, what would the what parameter estimates would you get? So if the I think the lambda parameter, if the lambda parameter in lasso loss is 0, what would your parameter estimates be? It'd be OLS. Great. All right. Good. You guys got that problem correct. Okay.
3 points.
Yeah. So you know, stuff like that. Okay. I'm not going to tell you what I'm going to ask, but it'll be something like that, right? So So that, you know, that's a conceptual thing where you have to understand what lasso is doing, and it's modifying the OLS loss function by adding on this thing. And but if you zero that out, then it's just the OLS loss. Yeah. Question.
All right. Well, first of all, for some reason the week 3 homework is due today. I was assuming.
No. That's a mistake. The week 3 homework is due next 1 week from today. Okay. Yeah. And I just posted the RMD thing. Yeah. And it's all on neural networks. Okay.
So, anyway, second question is, how many conceptual questions will there be? Like,
I don't. 1 page. Okay. I don't know.
I just want to know how many.
Well, all right. We'll say 6. Okay. I don't know. All right. Now I might. So wait, how many pages? I've got 7 pages, right? I've got 7 different topics here. I've got like 1, 2, 3, 4, 5, 6, 7. Okay. So probably each one of these things will be like 15 points. Okay. And then maybe conceptual, I'll make it worth 10 points or something. Okay. And then probably, all right, I'm just spitballing here. All right. So probably, 15 points each. I don't know, maybe one of these things will make worth 10 or something. And then conceptual questions, you're probably looking at like 5 questions, and I'll make them worth 2 or 3 points each. Okay. All right. Yes.
For regularization, the OLS loss, is that just to compare the lasso and the ridge loss to?
Yeah, I mean, the OLS loss is kind of, I don't know, it's like the grandfather loss function, right? It serves such a important loss function, right? Like it powers all of regular linear regression, okay? And so we're just saying like linear regression is great. It gives us unbiased estimates. It's got blah, 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 blah. It's great. And we're just saying like, but can I tweak it a little bit? So we use the OLS as a starting point, and we modify it by doing these things. Now, I don't know, what's another way? Like, there's something called a quantile regression, and I don't even know how it works, honest. I mean, I don't know what the loss function is for quantile regression, okay? But I think it uses the absolute errors. So OLS uses the squared errors, and then quantile regression, I think, uses the absolute errors, and so you get like a different fit. And so if you wanted to use that absolute errors as a starting point, you could also modify it. And I don't think it's been as deeply studied. I'm sure you could find a paper where somebody studied this thing. But because OLS is so popular, we often use it as a starting point. Anybody know why OLS is so popular? Like, why did we choose the squared errors and not the absolute values of the errors?
Absolute value is a sign that makes everything scary.
Yeah.
Well, I think it's because it prioritizes every error being equal to one another as close as possible, right?
So the absolute value errors will say all errors are equal, but the squared errors say bigger errors are worse than smaller errors. Okay. Now, so there's a few reasons why squared error is more popular than absolute error. Okay. One is absolute value is not differentiable everywhere, right? It's got that v, and so the derivative like breaks, and so when you try to plug it into calculus stuff, it breaks a lot of things. And so, but the squared function is it's differentiable everywhere, which is nice. Okay. The mean is the value that minimizes the squared distance or the squared deviations, right? So, and what does the median do? It minimizes the absolute deviations, right? We didn't learn this? Huh? You may have forgotten? I don't know. Okay, maybe. I don't know. So like if we have the points 1, 4, and 5. Okay, so the mean, the mean is what, 3.33? And then the median is, Okay, this is not the best. This is not the best thing. Let's do. Is this the one I want? Is there an applet here? Okay, I'll have to figure it out later. Okay, but anyway, yeah, if you measure the absolute errors, okay, here you get 1 and 3, and so you have a total of the sum of absolute errors, or absolute deviations would be 4. And if you pick, if I picked like this to be the median, okay, like 3, then I have error of 1. What is this? 1, 2, and 2. Okay, and this would go up to 5. So the median will give you the smallest absolute errors, whereas the mean at 3.33, this will give you the smallest of the squared errors. Okay. So anyway, that's the relationship between kind of our rules of deviations and whatever. All right. Oh man, we already spent 40 minutes just talking about the test. Okay. Okay, is that good? You feel like you guys can prepare? Yeah.
So in one of the lectures you mentioned about how loss prefers to push things towards 0 and ridge regression prefers to push it towards 1. Do you have to do all these little nitty-gritty?
I mean, those I would think are fair questions for the conceptual part. Okay. Okay. Like, I don't know. Am I gonna make you like graph stuff in a weird? No, but I think those are fair questions to ask in the conceptual section, right? Like the lasso will push all of them down towards 0. Ridge will kind of push them towards each other, and then shrink them because ridge penalizes like larger errors more than smaller errors. Things like this. Yeah. Yeah. Okay. All right. I guess we'll start on this stuff. All right. So, like a lot of this other stuff, we'll start with linear regression as kind of a starting point, and we expand on this, right? Okay. And so, this is all stuff but the way we estimate, the way we pick our estimator parameters or pick our coefficients for linear regression is that we're minimizing the sum of squared errors. Okay, so we're saying whatever W's will minimize the sum of squared errors, those are the W's that we're going to use. Okay, and we already did all of that work. And so, we do this by minimizing the loss function. So that's what we've done everything so far. So all of our first 2 weeks was all about minimizing some loss function, and we said, well, this is what happens if you change the loss function, that's regularization. And then, if we just take this for a more complicated example like neural networks, we're still just minimizing the loss function. That's how we train our neural network. We're just trying to say, like, minimize the difference between what the neural network's predicting and what our actual values are. Okay, the other approach is maximum likelihood. Okay, and so this should have been covered in your 100B. All right, and does anyone want to? All right, no, I won't put you on the spot. Okay, you guys remember maximum likelihood? Okay, we feel good about that? No? Okay, all right, well, maybe we can do something to help. All right, so in maximum likelihood models, you are modeling the error. Okay, you have to include the error term because now the observations themselves follow a probability distribution. Okay, the observations follow a probability distribution, and so each observation has an associated likelihood. All right, so maybe the model says this is what we predict, but really the value we see could be anything kind of spread around this predicted value. Yeah.
Is this what you tend to see in like real life data?
I don't know. You mean maximum likelihood stuff, or?
The fact that each observation has its own probability.
Yeah. So I guess everything comes down to what approach are we going to take, okay? So when we were doing this minimizing loss stuff, we actually didn't care about the probability distribution of any of this stuff. We just said, this is what my model's predicting, this is the actual data that I'm getting, and my ultimate goal is to make the values I'm predicting and the actual data I'm seeing to be as close as possible. I don't really care about the probability distribution of my data, okay? We kind of care a little bit when we are checking our assumptions. Like when we're checking our assumptions, there's like what is it, homogeneity of variance and I don't know, just all of this stuff, right? So those checking of assumptions is kind of where that probabilistic side comes in. But really the ultimate goal, even with the neural network, I don't even know what assumptions are going in there. The neural networks are just saying like, this is what I'm predicting, this is the actual value, let's just try to get them as close to possible as we can, okay? Over here, we're taking a slightly different approach. We are saying the values we observe come from some kind of probability distribution. Like this is the average person, but each individual is a little bit different. Some people are taller and some people are shorter and some people are, more this way and less that way or whatever, So we have some kind of probability thing that describes our population, okay? And now we're trying to figure out what is driving the population, okay? And that's this part, the relationship that exists in the population, but we also say, plus there's random differences, okay? This is kind of the central relationship, as people get taller, they weigh more, okay? That's the central relationship. But of course, there's individual differences. There's tall people who weigh a little, short people who weigh more, everybody in between. And so we're just saying there's also individual differences here, okay? And that's what we're doing in this, okay? And so, so really this error term, this epsilon, is just the key difference that we got, okay? So in the linear regression stuff, we said t hat, this is what we're predicting, and all we're doing is that each observation that we get is our prediction, which is the same for everybody with a particular x value, but there's also some error term, okay? And so, this is, I think, what you know, right? Actual value is prediction plus random error, or, this is often framed the other way. Error is actual minus the prediction, but that's all we've got, okay? Okay, so by including this random noise, suddenly our model is probabilistic, which means we've got a probability function to define all of this, right? Okay. And what are the rules about probability functions? Like a PDF? There's only two. One, it doesn't even have to be continuous. One is that it can never be negative, okay? It can never be negative. And number two, sums to one or integrates to one, okay? Those are the only two rules, okay? Whatever function you've got, if it fits those two, it can qualify as a probability function, okay? It can never be negative, has to integrate or sum to one. Okay, and so what we often do is we'll say our noise is Gaussian, all right? We'll say the random noise that we get is centered at 0 and has some variance term. And here I'm using sigma squared. So we've got some noise. Most of the time, it's centered around 0. So sometimes it's positive, sometimes it's negative. We've got kind of an equal probability of it being a positive or negative noise. It's got some constant variance, right? And this is basically when you are checking your conditions or assumptions for model checking in linear regression. This is basically what you're checking. You're trying to check to make sure that the noise is constant and whatever, homogeneity of variance. You don't want to see patterns, right? You just want to see everything centered at 0, random noise. That's what we want. Okay. All right. And so what we're going to do is we're going to say that by combining what the observations are, we can combine them and we can say each observation, therefore, comes from a normal distribution centered at what? The prediction line, which is W transpose X sub n, okay? So each observation we get it comes from a normal distribution that's centered at the line with some variance sigma squared. Yeah. Okay, and so maybe this is like a picture we've seen. Have we seen a picture like this? Maybe. Okay. So the idea here is here's some just data that we have observed. This blue line represents kind of the true relationship. Okay. W transpose X sub n. Okay. These are like the little arrows are to indicate that they're vectors. Okay. And the values that we observe are coming from a normal distribution where the center is on the line. Okay, so for this particular x value, the observations we might observe come from a normal distribution centered here, and they might be as high or as low as here, but values kind of in the values near the blue line are most probable, and okay. You have to kind of imagine this being in 3D and that this curve is coming out of the screen towards you or something. Okay, that's what this thing is. Okay, and we've got something similar here. For this for values at this location of x, we have a distribution centered at the blue line. Values higher or lower might be are also possible, but values near the blue line are the most likely. Okay, so that's what we have. So this is our linear regression model, but now made probabilistic. Okay, so now we can get a probability for every single value that we have. Okay, so this value that's very close will have a high probability. Okay, and this value that is far away from the line has a low probability, because according to the line it should be right here, but it's got a very big residual, so it has a low probability. But it was observed. Okay. Okay, and so so what we want to do is we want to estimate our parameters so that we will maximize the likelihood of the data we have. Okay, so this is the data we have. We want to say, we want the model that's going to maximize this. Okay, because we don't want to think of ourselves specially. We just want to think that this is just very likely data to come up. Okay. Okay, so. So if we just want to review maximum likelihood estimation, this is okay. So here's my bag. I don't even know why I'm bothering with this. Okay, but the idea is you've got some kind of bag here. All right, and inside this bag, I don't actually have marbles in here, but we're going to pretend that I've got 10 marbles in here. 3 of the marbles are red, the rest are blue. Right? Okay. And so when I draw one marble out with replacement, it's got like a Bernoulli distribution, and so we got a probability that we get a red marble is 0.3. Okay, so simple enough, yeah. And so the Bernoulli PMF, because it's discrete, is going to be this, right? So x either takes on 0 or 1, theta to the x1 minus theta to the 1 minus x. Okay, so we have probability 0.3. Okay, if we observe a sequence, red, okay, and we put it back with replacement, red, and we put it back, and then we scramble it up, and we pull out blue. Okay, so now we've got a sequence of 3 observations. Okay, we can ask what is the total probability of this exact sequence. Okay, and so these are independent events, so it's just the product of each of these things, right? So each one is IID, so the probability of this sequence is going to be 0.3 times 0.3 times 0.7. Yeah. Okay. So it's just the product of the PMFs. Okay, and we get 0.063. Okay. This is the difference. Well, the difference between a probability function and a likelihood function. Okay, so probability functions and likelihood functions, they both describe probabilities. Okay, here's the distinction. So a probability function is a function of the outcome x. So we say in the probability function, you can plug in a different x, and it will tell you what's the probability of that outcome, right? So you can say, what's the probability that I get heads, or I get tails, or you're plugging in the different possible outcomes, and it's going to tell you that probability. And the rule is that the probability function has to sum or integrate to 1 over all possible values of x. So you think of every single possible outcome that's possible, and all of those, whatever they are, they have to integrate or sum to 1. Okay? A likelihood function is basically the same function. It's going to look the same, except the thing that we are changing is the theta. Okay? We are changing the parameter of the function. We are not changing the outcome. We treat the outcome, the data that we've observed, as fixed. Okay? The data is fixed, the x is fixed, and we change the parameter theta. Yeah, question?
Yeah, I'm having trouble focusing. So
Okay.
The question is this just a rehash of 100B, or is there more?
Yeah, no, this part's a rehash of 100B because it's important for what we're talking about, okay? So, yeah.
I'll be back when we start.
Great. All right. See you later then. A likelihood function does not need to sum or integrate to 1 over all the possible values of theta, okay? So we can, so you can change the theta values, and you're going to get different values of the likelihood, but if you integrate across theta, you're not necessarily going to get 1, okay? All right, here's a quick question. Can a PDF have a value over 1? Like if PDF of x. PDF of x can definitely be over 1, okay? PDF of x can be over 1. A PMF, for a discrete distribution, cannot be over 1. So when you sum over all the values in a PMF, they have to add up to 1, so none of those values can be greater than 1. But a PDF, because it's an integral, right? So if you got a normal distribution like this, and then you got another normal distribution like this skinny one, its peak's going to go, you guys can't see over there. The skinny one can, what happened? They changed something on, I don't know. Okay, this used to be I click the button and I could draw on the screen, but all right, I don't know how to use my computer today. All right, Windows Update did something. I don't know what it's doing, honestly. Okay. All right, but basically, here, I'll just show you different normal distributions. Okay, so if I do normal distribution, okay, well, these examples don't go over 1, but they can go over 1, okay? Because the important thing is that the area integrates to 1, but the individual value, if it's really skinny, will go over 1, right? So, you know, for example, how do you get a PDF in R? Like if you want the, like if I want this value, so in R, if I want to know this value for particular x, the PDF of 0, what is the command I use in R? It's not pnorm. Dnorm, okay? The density, you're asking for the density. This is the density function, okay? What is this function? The CDF. The CDF is pnorm. The CDF is P norm. The PDF is D norm. What? Okay. Something. What's going on? Let me just show you. All right. Restart R, please. Don't break on me. My computer. What is... You are not my friend today. I disapprove. All right.
Maybe an answer crown.
Huh? He's jealous? Jealous. All right. Well.
Skill and task manager.
Yeah, I know, right? Okay.
More details.
There we go. There we go. Okay. I don't like killing things, okay?
You can unalive it.
Yeah, okay. There we go. All right. Let's try this. All right. So, okay. So if I do D norm of 0, what do I get? D norm of 0 is around 0.4, 0.3989, okay? That's the PDF. It's the height of this red bar, okay, or this red line, okay? It's around 0.4, okay? P norm, which is the CDF, P norm of 0 is what? You guys should all know this. 0.5, okay, okay? And what is Q norm? Q norm of 0.
0.5.
Q norm of 0. You guys are breaking my heart.
2. Wait, I don't know.
Don't just spit out numbers. Q norm of 0 is negative infinity, right? It is the value that you plug into x so that the cumulative probability is 0. Right? These are inverse functions. All right, let's just try a few others. All right, Q norm of 0.025. I'm 0.025. Q norm of 0.025. We should get this one right. Negative 1.96. Thank you. Okay. Q norm of 0.025 is negative 1.96 because this is the value. If I plug in P norm of negative 1.96, we would get 0.025, right? Okay. There we go. All right.
This is not coming out for the midterms.
No, but you should know this. If you're going to call yourselves a stats major and graduate from UCLA as a stats major, and you don't know the difference between D norm, P norm, and Q norm, don't tell people you went to UCLA, all right? You just got to, like, this is like, you've got to know this. You got to know this, right? You got to know the difference between your PDF and your CDF, okay? And the D norm is for the PDF and the P norm is for the CDF. Yeah. The CDF is the integral from negative infinity up to your x of the PDF, okay? What do you do with that? It's the cumulative probability. It's, yeah, it's the cumulative probability. It is, okay. Well, we use the CDF extensively in 102C. All right. So anyway, okay. So back to likelihood. Okay. So a PDF itself. So if I do a D norm of say 0, now how can I get D norm of 0 to go over 1? Standard deviation I can set to like 0.01. Okay. And if I set the standard deviation to 0.01, my D norm is now like 40, okay? 39, it's like it's 100 times bigger, okay? Because my standard deviation is 100 times smaller, okay? So that's easy, okay? But if I integrate d norm across all possible values, I will get 1, okay? However, integrating a likelihood function across all possible values of theta will not necessarily give us a value of 1, okay? It will never be bigger than 1, but it won't necessarily be 1, okay? So anyway, we're going to revisit this thing, all right? And this time, here's my big bag, okay? And there's marbles in here, okay? But this time you don't know how many marbles are red and how many marbles are blue, okay? And my question is, what you want to know is what proportion of marbles in the bag are red, okay? And rather than dumping them out, okay, you got to look at them one at a time, okay? So you reach in here, you draw out 3 marbles with replacement, okay? And you get this sequence, red, red, and blue, okay? And so based on this, you want to say, well, what is the most probable, okay, or what is the value of the proportion of red that will make this sequence red, red, blue, like very, very probable, okay? And so we would not say that if I got red, red, and blue, okay, we will not say that the bag is 99% blue, right? Because if the bag is 99% blue, then my sequence of red, red, blue is really, really, really unlikely, okay? At the same time, having the bag being only being 99% red is also unlikely because I did get a blue in there, right? So if it's 99% red, yeah, the red parts are likely, but that one blue is going to be incredibly unlikely, right? And so we want to say something in between. Is it 50% red and 50% blue? Okay, then that would be, 50% red, 50% red, 50% blue. I have a total probability of 0.125, okay? Or total likelihood of 0.125. Is it 40% red? If it's 40% red, it would be 0.4 times 0.4 times 0.6, okay, whatever that is. 0.4, yeah, 0.196, okay? Which is less than 0.25, so I don't want, or 0.4 times 0.4 is 0.16 times 0.6 is 0.096, okay, 0.096, okay? So 0.096 is less than 0.125, so that's not good, okay? If I go, is it 60% red, okay, then it's going to be 0.6 times 0.6 times 0.4, and that's whatever, 0.36 times 0.4, 0.144, okay? Which is better than 0.125. So we go, okay, we're in the right track, all right? So anyway, rather than having to do this guess and check thing, we're going to use calculus, right? And so anyway, we say, all right, we want to maximize this thing. For some unknown value of theta, our probability is theta squared times 1 minus theta. And we want the value of theta that's going to maximize this, okay? Now to do this with calculus, because it's a product, it's like messy, right? You take the derivative with product rule and chain rule and all of this stuff. It's a little bit messy. And so rather than taking the product of theta squared times 1 minus theta, we take the log, okay? And we say that the function that maximizes the log, or the value of theta that maximizes the log function, is going to be the same value that maximizes the original function, okay? Because the log is a monotonic, it's always increasing. If a is bigger than b, then the log of a is always bigger than log of b. So because of that, we can be confident that the value that maximizes the log function will also maximize the original function. So then we use calculus. This turns every products into sums. That's what logs do. And we go and we take the log of this, derivative of this, and we go through and we say, oh, the value that maximizes this is 2/3, right? So I kind of skipped over this, but this is the review part, right? Okay, and so we say, okay, if the bag is 2/3 red, then that's going to produce the maximum likelihood of the sequence that I got, red, red, blue. Okay, and any other value will give me a slightly lower thing. Now, is that good? Okay, so this is what we're going to do, but now we're going to apply it to the linear regression model. Okay, so the linear regression model says each observation comes from a normal distribution. It's centered at this regression line, and it has a variance of this constant. Okay, so I guess this is an assumption that the variance is constant, right? It's the same assumptions as regular linear regression. Okay, and if we assume all of our observations are independent of each other, which is often what we do in statistics, which I don't know if that's a good observation, but a good assumption, but that's what we do a lot because it makes our life easier. We will say that the total likelihood, the likelihood of all of our data, is going to be the product of each of these probabilities. Okay, so the likelihood is the product of the probability of each thing, and each of these probabilities is the normal distribution. Okay, so we're just going to say, you know, what's the probability of getting this t sub n if it's coming from this normal distribution? Okay. All right, and so if the PDF of the normal distribution is this, okay? Have you guys memorized this yet? Kind of? Okay. Really the only important part is the e to the negative x squared, okay? E to the negative x squared will give you something that looks like a normal curve, okay? And then the rest is just so that it integrates to 1. Okay. So anyway, we got this, the normal distribution. And so I will just plug in the PDF of the normal distribution right there, okay? So I just plug that into right there. And so now the total likelihood is the product of all of the individual PDFs, okay? So with when we are doing the total probability, I guess, I don't know, this is an important distinction, is that we multiply the PDFs, okay? And not the CDF. Right? We're multiplying these things, right? But of course, the probability, it's a little strange for a continuous distribution. The probability of any one observation is 0, but you can still take that density and multiply it. Okay, so anyway, we've got this this thing. This is the likelihood of all of our data. All right, so we took the product of all n observations, and this is where we are. And we want to find the W that will maximize this total product. Okay, and so this is where we are. So here's our likelihood, and here's the important things. Okay, everything here, okay, is fixed except for the W. So our values x, this is our observed data. That is treated as fixed. The observed values of t, basically the response there, is also fixed. Okay, so everything is fixed, and the variance is also a constant. The only thing that we can change is w. So we are going to change that, and we want to find the value of w that will maximize this. We're going to treat everything else as fixed. All right, so here is the total likelihood. And again, because this is a product, it's very messy to deal with. So I'm taking the log of this thing. Okay, so the log of a product is the sum of the logs, right? The log of a product is the sum of the logs. So the log of a times b is log of a plus log of b. Okay, so anyway, this is what we go. We get the log of this. So the log of this is negative 1 over 2 log 2 pi. This theta over here is negative log theta, and then the log of the exp just kind of kills all of that, and we just have everything on the inside. And then and we get this log likelihood here, okay? So if I distribute the sum, the n plus 1, n from 1 to n, okay, this is a constant, so it just becomes n times log of this, and this is a constant, so it becomes n times that, and then this is the only part that's not a constant, so the sum applies to here. Okay. All right, and so really we just have to worry about this part, right? Because this stuff, these are just constants, so I just need to worry about maximizing this stuff in here. Okay, so, okay, I guess this is what the slide said, right? Okay, so this is all a constant, this is a constant, so we just need to maximize this, all right? Now, what do we notice here? This part that we are trying to maximize, this is basically the same as the sum of squared errors, right? So, it turns out that when you want to maximize the likelihood function, mathematically it's equivalent to minimizing the sum of squared errors, because this has a negative value in here, right? So if we want to maximize this, we want to minimize this because there's a negative value associated with this. Okay, so minimizing the sum of squared errors and maximizing the likelihood end up being equivalent, right? Under the assumption that your errors are normally distributed. Okay. So if the errors are normally distributed, this is what your likelihood function or your log likelihood function looks like, and if we want to maximize it, we want to minimize this because it's being multiplied by a negative. So that's kind of neat, right? I don't know, maybe you're not impressed. Did you guys already do this in 100B? Yeah? Okay, all right, well, great. Not with the SSC? Okay, and I think this is just messy handwriting stuff to kind of show that indeed the math works out the way we did, okay? So if I did indeed want to do calculus to maximize this, okay? All right, so here so, you know, we already know the answer, but I just went ahead and I did the work. But it was like too much stuff, so I didn't want to like typeset it because it's kind of a pain to typeset everything in LaTeX. But so this, I hope you'll forgive me for having handwritten, okay? So here I'm taking the derivative of this with respect to W, okay? So these zero out because there's no W in there. And then, and this becomes this. The 2 comes down, and we multiply using chain rule times negative of x of n, and this negative will cancel that negative, okay? And we get this, and when we expand this, w times xn and xn transpose times w, those are both 1 by 1 vectors, so they are equal, okay? So I can distribute this as x transpose, xn tn right here, and xn right here. So I can swap these two around, and it's okay, and I'll get xn times xn transpose w, okay? And this the dimensions do line up. This is 2 by 1, and this is 2 by 1. All right. And then if I set this, if I get rid of the summation sign, this is what I get. And then if I want to set this equal to 0 and solve to maximize this, right? So I kind of skipped the writing of it, but here's my derivative. I'm going to set this equal to 0 and solve for the w that maximizes it. Okay, so we can do this. We'll set this equal to 0 and solve, and when we do that, we'll indeed get x transpose x inverse x transpose t. Okay, and so therefore, the solution that minimizes the sum of squared error, or mean squared and mean squared error, is equal to the values of w that maximize the log likelihood, or the likelihood function. Okay, and it's interesting to note that sigma squared, the size of the variance, as long as we assume it to be a constant, doesn't really affect our answer. Okay. You could, and I'm not asking you to do this, but if instead of trying to figure out the w's, okay, you could try to find the value of sigma that will maximize the likelihood of the data, okay? And that's also possible. And I think the book actually goes through that, and maybe actually talk about that here. Okay. All right, so this is kind of where we left off. All right, and we said all of this, And we said the values that maximize the likelihood will be the value that minimizes the sum of squared errors. Okay. And so here is, what if we wanted to do it so that we can maximize the likelihood with respect to sigma? Okay, so in the earlier thing, we found that W, the answer W hat doesn't depend on sigma, but what if I wanted to maximize my likelihood according to sigma? Okay, with respect to sigma. So I follow the same process, okay? And so here, here's the log likelihood, and now I take the derivative of this with respect to sigma, okay? And so what do I get? This zeroes out. N log sigma becomes negative n over sigma. And then this whole thing becomes 1 over sigma cubed times all of this, okay? This is a constant with respect to sigma. And then, and we're going to set this equal to 0 and solve for sigma. Okay, and what we get is that sigma squared ends up being 1 over n times this. So what's this? This is just the mean squared error, okay? So that's interesting, right? So sigma squared ends up being kind of 1 over n times the squared error. So the estimated variance is the value of the variance that will maximize this is the mean squared error, right? How is that different from sample variance? So if instead of instead of this thing W transpose xn, if I just had if this was y and this was y bar, okay, which is basically what I've got, what's the difference between this and variance?
Doesn't have to be one, right? I mean, it's an estimate variance.
So the only difference is that here we're doing 1 over n, and for sample variance it's 1 over n minus 1, right? Okay. So this is going to be biased. Yeah, this is going to be biased. If we're using it as an estimate of the population variance, but we're not. Okay, we're not using this as an estimate of the population variance. We're using it as the value of sigma that maximizes the likelihood of my data. Okay, we're using it as the value of the variance that will maximize the likelihood of the data that I have. Okay. Now you might say my estimate of the population variance is going to be the variance that maximizes the likelihood of my data. That's fine, but then there's pros and cons to that. Fisher information. You guys covered Fisher information? Anybody want to give me a description of what Fisher information is? Yeah.
All right. So there's a thing called the Kramer-Rao lower bound.
Okay.
Most of the important part of it is the denominator, which is Fisher's information.
Okay. And so what is that?
Kramer-Rao lower bound is the formula of the deepest depths of hell. You can look it up on Wikipedia.
Yeah. Okay.
Oh wait, no, it's like the lowest variance.
Efficiency. All right. Okay. All right. I will forgive you if you graduate UCLA with your statistics degree and you forget exactly the details of Fisher information, right? Like, if you get a graduate degree, then you got to know this. But bachelor's degree, I'll forgive you if you forget your Fisher information, right? That's just me personally. Probably other professors in the department, like Christo, will be upset. But I will be sad if you don't know the difference between P norm and D norm and Q norm. All right, I feel like that you got to know. All right. So Fisher information. All right. Let's go backwards. All right. So let's talk about derivatives. Okay. What does a derivative tell us? I guess I already wrote it here, okay? But the derivative is like your slope, right? It's the rate of change of the function, right? So if the function suddenly gets really steep, your first derivative becomes more positive, or becomes a larger value, right? Okay, and then what does the second derivative do?
changes?
It tells you how quickly the slope is changing, right? So this is like in physics, it's like your acceleration. It's just telling you how quickly that slope is changing, which can be thought of as the curvature, right? So if you've got a function with steep bends in it, okay, your second derivative will have large values, right? And meanwhile, if your slope, even if you have a very steep slope, if it's constant or if it's barely changing, your second derivative is very small, right? So if we're talking at like, if your airplane is cruising at like 600 miles per hour, okay, your rate of change in terms of the, relative to the ground is changing rapidly, but the acceleration at that point is pretty small, right? Okay, so a large second derivative, okay, or a large absolute value of the second derivative gives us information about the curvature, how sharp or pointy it is, okay? It also gives us stuff about like if it's concave up or concave down, and if it's like maybe an inflection point. We've got stuff like that, right? Okay, so anyway, this is what we have. All right, and then here we're talking about gradients. All right, and so we can kind of generalize some of these ideas of regular unidimensional derivatives to gradients, okay? So so here's the gradient, and so the gradient, which is kind of the first derivative, kind of the parallel of a first derivative, would be the direction of steepest slope, okay? All right, and if I take the derivative of this, or the gradient of this, okay, so the gradient of the gradient, which is like the second gradient, kind of, all right, it's kind of like the second derivative, right? So you're taking the derivative of derivative. So now we're going to take the gradient of this gradient, okay? It's kind of like the second gradient, but we give it the name, we call it the Hessian, okay? We kind of remember this? Okay, so here's what we call the Hessian, and it's going to be an n by n matrix, right? So if your function returns a scalar, your vector is n-dimensional, so your gradient is a vector of length n, and the kind of the second gradient, the gradient of the gradient, the Hessian, is going to be the basically all the partials of each element, and so it's going to form an n by n square matrix. Okay, so this has n elements in it, and basically we're going to take the partial derivative of this first element with respect to w1, then respect to w2, all the way up to wn. We take the partial derivative of the second element with respect to w1, then w2, all the way up to wn, and we take the partial of this with respect to w1, w2, all the way up to wn. Okay, and so that's what we have. Okay, so we have partial squared with respect to w1 squared, and then here's partial 1 of w1 with respect to w2, and all of this, okay? So we got all of this. And we can kind of think of this as a multivariate generalization of the second derivative. All right, so, okay, yeah, I guess this is exactly what I said. All right, so this is like, if you were to have to find the Hessian manually, you would first take the partials with respect to each element first, and then you take each of those things and do the partials with respect to each element again. All right, so so why would we want to do this, right? So just like the second derivative gives us information about the curvature of the function, the Hessian also gives us information about the curvature of the function. Okay, and so if we apply this to the likelihood or the log likelihood function, it will give us an idea of the curvature of the likelihood function. All right, so what does that even mean, right? Basically, if there's high curvature in the likelihood function, we can have a lot of confidence in our parameter estimates. All right, so let me just do like a silly, simple example. All right. So here, we're going to go back to our mystery pouch. Okay, we go back to our mystery pouch. We've got an unknown quantity of red and blue marbles. All right, and here I go in and I take out 10 marbles with replacement. I take out 10 marbles with replacement, and 4 are red, 6 are blue. Okay, so the likelihood of that sample of data is going to be theta to the 4, 1 minus theta to the 6. Okay, and I can graph this. And what will this likelihood function show? What will it look like? What are the bounds of theta? What's the largest value theta could possibly be? 1, and the smallest value theta could possibly be 0. Okay, and what is the likelihood that theta is 1? 0, right? Theta cannot be 1. All right, if I observed 4 red and 6 blue, theta cannot be a proportion of 100% red, and likewise, it cannot be a proportion of 0% red. Okay, what's going to be where's the peak of theta? What's going to be the most probable or most likely value of theta? Just intuitively, you would say 0.4, right? 0.4. We got 4 red out of 10. Okay, so intuitively, the most likely value is going to be 0.4, and that's what we'll see. Okay, so we've got this. All right. The graph got cut off. Okay, but the peak here is this. This is 0.4. This is 1, and this is 0. But what this also shows us is that if I dumped all of the contents of my bag out and we counted up all the red marbles and blue marbles, and it turns out that it was 50% red and 50% blue, would any of you be shocked? No, right? Because I got 4 red and 6 blue, and if it turned out to be 50-50, you wouldn't be shocked. It's like, that makes sense. Just by random chance, I happen to get 1 more blue and 1 less red or something like that, okay? And also at the same time, if I dumped it out and it turned out to be like 30% red, would any of you be shocked? Not really either, okay? And it's really only until we get to like, oh, it turned out to be 80% red. Okay, you'd be like, whoa, that's kind of weird that I got 4 red and 6 blue. Or if I told you it was only like 10% red, you might be like, oh, that's surprising that you got 4 red and 6 blue or something like that, okay? So basically, when I say the most probable value of the proportion red is 0.4, that's true. But we're also not super confident about this estimate, okay? Saying that it's 0.4, we're like, okay, it's 0.4, but if it's 0.5, that sounds reasonable. If it's 0.3, that also sounds reasonable, okay? And that's basically what this slide says. Okay, this time we're gonna do the same thing, but we have a lot more patience and a lot more time. And we draw from my bag 1,000 times, okay? And after 1,000 draws, I got 400 red and 600 blue. Okay, 400 red and 600 blue. Okay, what is the value of theta that will maximize this data? It's going to be 0.4, okay? What will our likelihood curve look like, though? How will this be different? So when I only had 10 draws, this is what my likelihood curve looked like. When I have 1,000 draws, what do you think the likelihood curve will look like? Okay, yeah, it's going to be a lot more narrow, okay? And what this tells us is that if you drew 1,000 marbles and 400 were red and 600 were blue, then the proportion of red in this bag is going to be really close to 0.4. Okay, if it turned out to be 50% red, that would be shocking. Okay, if it turned out to be 30% red, that would also be shocking, because if it was truly 50% red, for me to get 400 red means like something really weird happened. Okay, I probably wasn't random sampling. Okay, something strange. Okay, and really the only values that wouldn't really be shocking would be values like 0.4, 0.39, 0.41, maybe 0.42 is okay. But really, like once you start veering away from 0.4, the likelihood really drops off. Okay, so to kind of express this in the terms of what we're talking about, we will say that the curvature of this function is much greater than the curvature of this function. Okay, so we can see how rapidly this slope changes. It's going, the slope here is super steep up, and then suddenly it's super steep down. Okay, so it's like 0, and then suddenly it's skyrocketing up, and then it's skyrocketing down. It's shooting up. So the change in the slope is very rapid here. Okay, which means we're going to have a very large second derivative. Over here, it's a lot more gentle. Okay, slopes up, slopes down. Okay, and especially if you look at the size of these, well, actually, no, that doesn't even matter. But basically, the curvature is very great here. Okay, so I use this term pointiness, but basically, you know, this one is a lot more pointy, so there's a lot higher curvature. Okay, and so as far as the variance in what theta can be is a lot smaller. Okay, so we have a lot more confidence in our estimate of 0.4. All right, so how is this going to be reflected when we look at the Hessian? Okay, or you know, if we look at the second derivative of these things, okay? So in the second derivative, because it's unidimensional, right? So we look at the second derivative here for with only 10 draws, our likelihood function looks like this, and our log likelihood function, our log likelihood function looks like this, and the second derivative will look like this. And for 1,000 draws, basically it's the same math, but it's basically 100 times greater than what we have here. So the second derivative of our, with 1,000 draws is 100 times greater than what we have over here. Okay, so so if I plug in this value, 0.4, which is currently our estimate of theta, okay, the second derivative here is negative 41, and the second derivative here is negative 4,167. Okay, so we have a lot more curvature for the second derivative here. All right. So this idea of curvature as a measure of information is useful to us. Okay, so the fact that the second graph had a lot more curvature, was a lot more pointy, tells us that we've got more information about the location of the theta. Okay, in both cases, our best guess for theta was 0.4. Okay, whether when I had 10 observations and when I had 1,000 observations, in both cases, my best estimate for theta was 0.4. But when I've got 1,000 observations, I'm basically saying I've got 100 times more information about the location of theta than when I only had 10 observations. Okay, because here this value is negative 42, and this is basically negative 4,200. All right, and so this same concept generalizes to the multivariate nature of what we're doing. Okay, so if we're not dealing in one variable, okay, we can be dealing in a multi-dimensional, multivariate context. But and so the second derivative, okay, or the parallel to the second derivative would be the Hessian matrix. Okay, the Hessian matrix, and so so this is what we've got. If the log likelihood is twice differentiable, like if we can take the derivative of the log likelihood twice, then the Fisher information is equal to the negative of the expected value of the second derivative of the log likelihood. Okay, so this second derivative of the log likelihood, we can think of that as kind of the Hessian, and if we are able to take the expected value of that across all possible values of theta, okay, then that will give us what our Fisher information is. Okay, so we can think of this as kind of the expected value of the second derivative of the likelihood function. Okay, so if we think of how pointy or how much curvature is there in my log likelihood function or likelihood function or whatever it is that we're talking about, okay, in this case it's the log likelihood function. If we think about how much curvature there is in that, the Fisher information is related to that. Okay, so the amount of information that we have about our parameters is related to how much curvature there is in the log likelihood function. All right, so here's just kind of going back to our single parameter example. All right, this is what the expected value of the log likelihood looks like. Okay, so here is for a Bernoulli experiment. The log likelihood is this. Okay, and we would have to ask what is the second derivative of the log likelihood is this, and we have to ask what is the expected value across all possible values of theta. Okay, and so here x, the expected value of x with across all possible values. I'm sorry, what am I saying? Yeah, the expected value of x, okay, given theta here is theta, and the expected value of this is 1 minus theta. I'm sorry, yeah, this is the expected value of x with respect given a theta value. And so our Fisher information is this 1 over theta times 1 minus theta. And that's what we have. Fisher information itself is additive. So if you have more observations with the same likelihood, you can just multiply by n. All right, so here we'll look at the multivariate context. Okay. And so we've got the matrix of second derivatives, and that's our Hessian matrix. Okay, and the Fisher information is the expected value of the Hessian matrix of the log likelihood. All right, so that's going to be it's a little bit messy. It's a little bit messy. All right, so here we've got the likelihood function for linear regression, and we've got the log likelihood, and it looks like this. And we're going to take the second derivative of this with respect to w. Okay, so when we take the derivative with respect to w, this term zeroes out, this term zeroes out, and this term becomes this. Okay. So you can, I skipped a lot, but basically it becomes this, and via chain rule, you end up multiplying by x of n. So the two, I guess, in the textbook it fully expands all of this out. Okay, so we'll kind of leave that, and then so we'll just jump to here. I mean, this was done on an earlier slide. So this is the derivative with respect to w, and if we take the second derivative, this with respect to w again, okay, this term will zero out, and we just get x transpose x. So this is the second derivative of our log likelihood with respect to w. All right, and so the Fisher information is going to be the expected value of this Hessian, okay? And if we ask, what is the expected value of this, the negative of this, this is just a constant with respect to w, so we just end up getting this, okay? So the Fisher information is going to be 1 over sigma squared times x transpose x. And basically the final conclusion here is that if you've got a large variance for the random noise, you're going to have less information because this is in the denominator. Okay, and that makes intuitive sense. If there's a lot of scatter around the kind of the mean trend line, okay, the regression line, you're going to have less information about the locations of W, okay, W1, your slope and intercept. You're going to be a little bit less confident about that. Whereas if there's less scatter, okay, you've got a lot more confidence in what your slope and intercept are. Okay, and this is basically I just drew this picture where here there's very little scatter, and so one of these things is the true relationship, but the different fits, like if we have different lines, they all end up having similar slopes and intercepts, and so whatever we get, we can be pretty confident that it's close to the true value. Whereas if there's a lot of scatter, you might have quite varying different slopes and intercepts, and so you're going to be a little bit less confident. I mean, this is all intuitive, okay? That if there's a lot of scatter in your data, it shows up this way, okay? But it ties it back to Fisher information, which I think is a little bit of a harder concept to grasp, and so I don't know if it helps to just kind of isolate it and say, if we think about the curvature of the likelihood function and how how pointy that thing is, that's basically related to how much information we have. And if there's high curvature, you're going to have more information. And if there's a lot less curvature, you're going to have less information about your data points. Is that good? All right, we'll end here for today. Today's stuff is not, it wasn't any of the topics that I listed for the midterm exam. So we'll see you guys on Wednesday for the midterm. Good luck as you guys study, and then we'll pick up next Monday in terms of lecture topics there. All right, have a good couple days as you study.